A small, clean darkness slides across a distant star. Not an eclipse the way we know it. No edge you could point to with a finger. Just a measurable, dimming, precise, repeatable, happening far beyond our solar system, where the exoplanet WASP-39b moves on schedule. For a few hours, starlight doesn't simply pass by a world, it passes through it. That is the cosmic trick. At the center of this story, the atmosphere becomes a filter. The planet becomes a test. The transit is real. The dip in light is real. And if we're careful, the faint changes across wavelength can be real clues about chemistry, about what an exoplanet atmosphere is made of, and what it can pretend to be. WASP-39b is a kind of generosity from nature. Not because it's gentle or because it's remotely habitable. It isn't. It's hot. It's swollen. Its atmosphere is extended, puffed up enough that in principle it should leave a stronger signature in spectroscopy than a smaller, tighter world. A thicker atmospheric rim means more starlight is altered, which means the fingerprints should stand out a little more clearly. So here's the paradox, right? At our cosmic checkpoint, if this is a relatively forgiving target, if this is in a sense the training ground, why did the spectrum still trigger doubt? Because the universe doesn't grade on a curve. Even when the target is easy, the measurement is brutal. You're not measuring a color. You're measuring a whisper of a difference in how much starlight makes it through at one wavelength compared to another. You're measuring the boundary between signal and artifact. And that boundary is where a claim can be born, or where a false positive can quietly assemble itself out of good intentions and imperfect instruments. This is where the title's promise first bites down NIRSpec line by line on WASP-39b SO₂ versus systematics, the full story. The point isn't just that an exoplanet atmosphere can be read, it's that even a world like WASP-39b can produce a signature that refused to fit until every possibility planet star and instrument was treated like a suspect. That phrase, SO₂ versus systematics, isn't a slogan. It's the central tension pair in plain language signal versus artifact. Picture the spectrum as a barcode drawn in faint shadows. Each line is not a flourish. Each line is a potential molecule if it's real, and a potential mistake if it's not. And this is why we start here, because the search for signs of life biosignature claims, and even the faint edge case ideas of technosignature gases, will rise or fall on whether we can trust this kind of evidence, not as belief, as procedure, as restraint, as a chain of reasoning strong enough to carry hope without snapping under it. For WASP-39b, the stakes are not life, the stakes are credibility. If you can't win the argument on a loud, inflated atmosphere, you have no business whispering about a temperate, rocky exoplanet in the habitable zone. If you can't separate a real atmospheric signature from instrument systematics here, then detection elsewhere becomes a word with a hollow center. So we anchor ourselves in what is solid. During a transit, the measured starlight changes. Spectroscopy can separate that light into wavelengths where gases absorb. And yet here's the quiet menace. Those same wavelength by wavelength structures can also be shaped by things that are not the planet at all. This is the first explicit confounder we have to name, even before we descend into details instrument systematics. Thermal stability, detector behavior, wavelength calibration drift. The subtle ways an instrument can add patterns that look like chemistry. In other words, model fit versus calibration drift. An exoplanet atmosphere versus contamination by our own measurement process. It's tempting to imagine the data as a clean signal arriving from a clean world. But in practice, the data arrive wearing fingerprints from every step they touched on the way to us. That's not cynicism. That's physics. That's the price of precision. The higher our sensitivity, the more we must care about small system behaviors that used to be invisible. And still, despite that, we go forward because this is exactly how we learn to see. Now hold that silhouette of WASP-39b against its star. Hold the idea of a barcode emerging from the dimming. And hold the title's central conflict in your mind, SO₂ versus systematics, a signal that refused to fit until the machine was interrogated. Because the next step is not wonder. The next step is workmanship. We enter the machine room where the raw light becomes a spectrum line by line, and where the difference between an exoplanet atmosphere and a false positive can be just one stubborn pattern that won't behave. The detector doesn't give you a story. It gives you a flood of tiny numbers, starlight recorded as a pattern of brightness frame after frame, while an exoplanet crosses its star. In the beginning, it's almost insultingly plain. A star, a slight dimming, a time series. But the moment you ask for chemistry, the simplicity fractures. You're no longer watching a single light curve. You're slicing the starlight into colors, into wavelengths, until you're watching hundreds of little light curves at once. Each one is its own fragile measurement. Each one carries its own vulnerability to instrument systematics. This is the line-by-line promise in the title and the trap inside it. NIRSpec line-by-line on WASP-39b isn't a poetic phrase. It's a workflow. It's the act of treating the spectrum like a sequence of evidence points instead of a single blended color. And it's the reason the SO₂ feature could feel so present, yet still refuse to fit cleanly until the full chain was tested. Here's what "how we know" means. In this context, we accept that the telescope doesn't detect SO₂. It detects light. During a transit, a thin layer of the planet's atmosphere filters that light, so the apparent size of the exoplanet changes slightly with wavelength. A gas that absorbs at a particular wavelength makes the planet seem a little larger there because less light gets through. That's the basic logic of transmission spectroscopy. But the basic logic is not the same as a reliable conclusion. So we build an evidence chain step by step, and we refuse to skip the steps just because the result feels satisfying. First comes the raw measurement brightness on the detector as a function of time. The transit creates a dip. That dip is the backbone. But when you expand the measurement to line by line, you are also expanding the number of ways things can go subtly wrong. A small change in the instrument's behavior can masquerade as a small change in the planet's apparent size. A calibration drift can look like a molecule. That is why before we ever say SO₂, we have to say calibration. We have to say corrections. We have to say, what did the instrument do while we were looking? The title itself demands it: SO₂ versus systematics, not SO₂ as a trophy. SO₂ as a suspect that has to survive a hostile cross-examination. Then comes the spectrum, a plot of transit depth versus wavelength. If you imagine the planet as a silhouette, this is the silhouette's tiny change in width as the light shifts in color. You don't see clouds, you don't see wind, you don't see oceans. You see a curve with bumps and slopes and uncertainties. Now comes the moment where many documentaries cheat. The moment where a label appears on the curve, SO₂, as if the line announced its own name. That's not how it works. What comes next is a translation process called retrieval. It's not magic. It's an argument between models and data. Retrieval uses forward models, mathematical predictions of what an exoplanet atmosphere would do to starlight for a given mix of gases and temperatures, and then asks which combinations best match what was observed. The output is not a single answer. It's a distribution. It's uncertainty turned into a shape. This is where honesty matters most. Because the word best can hide a lot. A retrieval can fit the data while still being wrong in its story about the atmosphere. Not because scientists are careless, but because nature allows multiple explanations that overlap. A particular pattern could be explained by one gas at one abundance, or a different gas at a different abundance, or by a temperature profile you didn't anticipate, or by a haze layer muting everything. The data can be honest and still not be uniquely interpretable. So the second half of how we know is not just we ran a retrieval, it's we stressed it. This is the first major limitation we must name clearly because the outline insists on retrieval priors and model assumptions. Priors are what you assume is plausible before the data speak. Model assumptions are the simplifications you choose because you have to like treating a whole planet's atmosphere as if it can be represented in one dimension, or as if it's in chemical equilibrium, or as if temperatures vary smoothly in a particular way. These assumptions are not optional, they're the scaffolding. But scaffolding can also tilt a building if it's biased. So when the title says the signal refused to fit one possibility, is that the universe was telling us something real. Another possibility is that our scaffolding was wrong. And alongside model assumptions sits the other confounder with teeth instrument systematics, drift, detector effects, wavelength calibration errors. At the precision needed for exoplanet spectroscopy, these aren't footnotes, they're rival explanations. A small wavelength-dependent artifact can imitate the very thing we're looking for, the rise and fall of absorption features that look like chemistry. So how do we grow confidence without pretending certainty? We look for stability. A credible gas interpretation should be robust. It should persist when reasonable analysis choices change, when alternative models are tested, when the data are partitioned and rechecked. Not because any one test is perfect, but because real atmospheric absorption behaves like physics across contexts while artifacts tend to shift when you touch the method. This is the edge of certainty discipline. It's the difference between we saw a feature and we have a case. And it's why WASP-39b matters beyond itself. Even though it's not a habitable zone world, it is a rehearsal for the future for biosignature and technosignature discussions that will live or die on whether we can separate planet atmosphere from everything that can contaminate it. Now hold the title's thread again tightly. NIRSpec line by line on WASP-39b SO₂ versus systematics, the full story. The full story is not just the claim. It's the chain of calibration, retrieval, and confounder testing that makes the claim worth listening to. And now we make the turn the outline demands. Because the next step is not to admire the spectrum, it's to distrust it strategically, to change perspective, to ask what would happen if the planet signal is partly the star or partly the instrument wearing an atmospheric mask. We step out of the glow of the conclusion and into the shadow where artifacts are born and where a real SO₂ signature has to prove it can't be explained away. A spectrum can feel like a confession, a clean curve, a set of dips and rises, a pattern that seems to say plainly, this is what's in the exoplanet atmosphere. But that feeling is dangerous, because a spectrum is also the perfect place for a lie to hide, especially a lie made of honest noise, subtle instrument systematics, and the quiet complexity of a star that is not a uniform light bulb. So we change perspective. We stop treating the feature as an answer and start treating it as an accused. This is the limitation-heavy heart of the story, the part that makes the title's tension real SO₂ versus systematics, a signature that refused to fit until every other explanation was allowed to take the stand. The question here is simple and it's brutal. How do we tell a molecule in the planet's atmosphere from a pattern created by our tools and assumptions? We name the tension pair out loud in plain language signal versus artifact, planet atmosphere versus contamination, model fit versus calibration drift, and we build a suspect list. First, suspect instrument systematics. At this level of precision, the instrument itself can draw shapes. Thermal stability changes can tilt baselines. Detector behavior can add wavelength-dependent quirks. Wavelength calibration can slide just enough that a line appears shifted, broadened, or oddly emphasized. These are not dramatic failures. They're small, plausible behaviors that produce big interpretive consequences when you're reading starlight line by line. This is where the phrase "refuse to fit" earns its ominous weight. Sometimes a feature refuses to fit because the planet is complicated. Sometimes it refuses to fit because the instrument is quietly imposing a pattern that the retrieval tries to explain as chemistry. So the first courtroom test is not, does the model match the data? It's, does the feature survive when you change how you correct the data? Does it persist when you do the careful, unglamorous work of asking whether you've built the spectrum on a shifting floor? That's the evidence moment in this section, not a new result, but a diagnostic posture. The feature is not treated as truth until it survives attempts to make it disappear. Second suspect, clouds and hazes degeneracy. Even if the spectrum is perfectly measured, an atmosphere can hide its own chemistry behind aerosols. Clouds can mute features. Hazes can reshape slopes. Scattering can flatten the very contrast that would otherwise make identification straightforward. That creates a different kind of false positive, not a fake feature, but a misread feature. A retrieval might compensate by inventing more of one gas or less of another to explain what's actually just a veil. So we add another tension pair detection versus interpretation. You can detect that the spectrum changes with wavelength and still be wrong about why. Third suspect, retrieval priors and model assumptions. This is the confounder that feels least physical, but it can be just as powerful. Retrieval is a disciplined guess, and disciplined guesses still have biases. A one-dimensional model can stand in for a three-dimensional world. Equilibrium chemistry can stand in for disequilibrium processes. Temperature profiles can be simplified to a few parameters. These assumptions are built into the scaffolding of inference. They can also steer a solution toward a familiar story, especially when multiple stories fit. This is how a feature can refuse to fit until you change the assumptions, and then suddenly it fits beautifully. The beauty can be real, or it can be the elegance of a model, finally finding a comfortable explanation that the data can't uniquely exclude. So we insist on a harsh rule. If the conclusion depends on one narrow set of assumptions, it's not a conclusion yet. It's a proposal. Fourth suspect, stellar contamination, the star itself. The star is the light source we're using as a backlight. But stars are not smooth, uniform disks. They have spots and faculae regions that are cooler or hotter, darker or brighter. If the exoplanet transits across one kind of patch, but not another, or if unocculted spots exist elsewhere on the star's own spectrum can imprint a chromatic signature that looks like the planet's atmosphere. This is the most unnerving suspect because it's not an error. It's astrophysics. It's the universe adding complexity at the source. So we state the tension pair plainly: planet atmosphere versus star contamination. A planet does not just filter starlight, it samples starlight. And if the starlight is heterogeneous, the sample is biased. Fifth suspect line, misidentification and incomplete line lists. This is quieter, but lethal. Line by line depends on having the right molecular fingerprints to compare against. If a database is incomplete, or if lines overlap in confusing ways, a feature can be labeled incorrectly. A real absorption dip can be given the wrong name. Or a model can attribute power to a molecule because the alternative fingerprints are missing or mismodeled. So even when the spectrum is real, the label can be wrong. And then there's the suspect that hides behind time itself, time variability versus sampling. If you only have a limited window, few transits limited baseline, small changes can masquerade as stable patterns. Or stable patterns can be overinterpreted because you haven't watched long enough to see them wobble. Ephemeris errors can smear signals. Baseline choices can emphasize features. The less you sample, the easier it is to mistake a snapshot for a law. This is the anatomy of a false positive, not as a single mistake, but as a conspiracy of small effects that all point in the same direction. Now here's the emotional core of this section. Good science doesn't protect the signal. It attacks it. If SO₂ is real, it should behave like physics. It should be consistent with expected absorption structure. It should persist across a reasonable analysis changes. It should not evaporate when systematics are accounted for. If it survives at the end, the burden shifts not to certainty but to credibility. If SO₂ is not real, it should be fragile. It should morph when calibration choices change. It should align suspiciously with known instrument behaviors. It should fade when alternative explanations are taken seriously. That's what artifacts do. They depend on the method more than the world. This is why the title doesn't say SO₂ discovered. It says SO₂ versus systematics. It's a contest between two explanations that can both produce a similar looking curve. And the feature refused to fit until this contest was fought honestly. We don't need to pretend the courtroom always delivers a single verdict. Sometimes the verdict is most likely with an asterisk. Sometimes it's consistent with not proven. But the process itself is the point, because this is the same courtroom where future biosignature claims will stand trial. And if we skip these confounders here, we will be defenseless later. So we gather what remains after the attempted demolition, after the suspects are named, after the tests are applied, after the easy narrative is denied. What remains is not triumph. It's the best supported reading of an exoplanet atmosphere we can honestly defend right now. And that is where we go next, to the careful, bounded statement of what the spectrum most honestly says about WASP-39b. What we know, what we infer, and what still depends on the scaffolding. The spectrum returns to the screen like a quiet verdict, lines and slopes with uncertainties and not declarations. It isn't a photograph of WASP-39b. It's a record of what starlight did when it passed through an exoplanet atmosphere, and what that behavior implies when you've tried in good faith to explain it away. This is where we owe the viewer something precise, the best current conclusion, and the boundaries around it. Because the title never promised a miracle. It promised a standard of proof. In our NIRSpec, line by line, on WASP-39b SO₂ versus systematics, the full story. The full story is not a single sentence. It's the discipline of saying what the data most strongly supports and refusing to claim more than that. So what does the spectrum most honestly say? First, it says the atmosphere is not silent. The transmission spectrum contains molecular structure, wavelength-dependent features, consistent with the chemically active hot exoplanet atmosphere measured through spectroscopy during transit. You don't have to name every constituent to recognize the central fact the planet's apparent size changes with wavelength in a way that is not flat, not featureless, not random. That matters because it means the method is genuinely sampling the atmospheric limb. It means we're not just watching a transit, we're extracting composition-linked information from it. Second, it says that when we interpret those features, we are always doing two things at once, detection and interpretation. Detection is the measured structure. Interpretation is the story we assign to it through retrieval. And this is where SO₂ enters again carefully without theatrics. In the best current reading, SO₂ is a compelling interpretation of part of the measured structure, not as a slogan, as a match between an observed pattern and expected absorption behavior that remains persuasive after the kinds of checks we described after the feature has been forced to defend itself against systematics, against alternative modeling choices, against the possibility that it's just the instrument or the scaffolding talking. That remains persuasive phrase is important. It is not the same as beyond doubt. It's a statement about robustness under interrogation. Because the entire emotional engine of the title, SO₂ versus systematics, is the fear that the most satisfying label might be the wrong label. The feature refused to fit until the analysis treated systematics like a rival hypothesis, not an inconvenience. The conclusion is worth hearing only because that rivalry was taken seriously. Now we widen the frame, just a little still staying inside the exoplanet atmosphere. Retrieval doesn't just name a gas. It tries to constrain a world. When retrieval works well, it can yield broader properties. How enriched the atmosphere is in heavier elements compared to hydrogen. How temperature might vary with altitude. How certain chemical ratios might be consistent with formation histories. But we say this honestly, those are not direct measurements. They are inference layered on inference. They depend on the model family you allow and the assumptions you make. So here is the limitation that must sit inside the conclusion. Like a warning label retrieval priors, and model assumptions remain a ceiling. This is not academic hair splitting. This is the difference between the data require SO₂ and SO₂ is the best explanation within a set of plausible models. A one-dimensional model can approximate a three-dimensional atmosphere, but it cannot capture everything. Equilibrium chemistry can be a useful default, but nature can deviate. Temperature profiles can be parameterized, but they can also be more complex than the parameters allow. These assumptions are embedded in the retrieval process. Different plausible assumptions can shift inferred abundances, even when the underlying spectrum is the same. So we keep the tension pair alive, even as we conclude detection versus interpretation, model fit versus calibration drift. Not because we're undermining the result, but because this is what intellectual honesty looks like at the edge of certainty. Now, the deeper reason this matters beyond WASP-39b is that every future claim about signs of life will come wrapped in the same structure. If a future spectrum from a smaller world in the habitable zone shows something tantalizing, a putative biosignature pattern, or a speculative technosignature gas, our first question will not be, is it exciting? It will be, does it survive this level of skepticism? That future moment will demand multi-gas context, broader wavelength coverage, and confounder testing so strict that it feels almost unfriendly. WASP-39b is not the life story. It is the training in how not to fool ourselves. So in plain language, the best current conclusion is this. We have a real atmospheric spectrum from an exoplanet. It contains molecular structure consistent with a rich atmosphere. Within the current best supported analysis chain, SO₂ is a compelling interpretation of part of that structure. And the credibility of that interpretation rests not on a single fit, but on its survival against systematics and against reasonable alternative modeling choices. Then we stop. We don't turn inference into certainty. We don't let the elegance of a model become the authority of a fact. We keep the uncertainty visible because it's part of the result. And now we take one step back because the outline demands a final turn of meaning. What does this painstaking case teach us about the next harder targets? About worlds where the signal is smaller, The confounders are louder, and the words biosignature and false positive will sit in the same sentence every time. We leave the spectrum on screen, model overlaid residuals, staring back, then let it fade into the question that follows us into the last section. When we say detected, what do we really mean? And what is still left to measure? A thin barcode of light hangs in darkness lines. That means something, lines that might mean something, and lines that only look like meaning when you want them to. Then the plot dissolves. The curve fades, and we're left with what the measurement always was: starlight handled carefully, trying to tell the truth through layers of uncertainty. This is where the story becomes quiet, not because the science is finished, but because the most honest part of exoplanet science is knowing what you have not yet earned the right to say. The title promised a confrontation, not a celebration. NIRSpec line by line on WASP-39b SO₂ versus systematics, the full story. And the full story is that the hardest work comes after the feature appears. The feature refused to fit until we treated every other explanation as real competition. That refusal is the point. It's the moment where curiosity becomes discipline. So what does this case change? And how we should talk about signs of life in exoplanet atmospheres. It changes our vocabulary because the word detected is often used like a gavel, as if it ends an argument. In reality, detected is the beginning of a different argument, an argument about interpretation, about contamination, about what physics can mimic what chemistry. WASP-39b is not a habitable zone world. It is not a biosignature stage, but it is a rehearsal for the emotional pressure that will come later when a future spectrum tempts us with a pattern we desperately want to be true. That future pattern might involve biosignature candidates, or even technosignature ideas like industrial gases in an atmosphere. And if that day comes, the lesson from this SO₂ case is almost stern. The first duty is to ask how we could be fooled. That is not pessimism. It is how discovery survives. Here is what we can say without overreach. Atmospheric interpretation lives under constraints. Instrument systematic stellar activity and model assumptions shape what we can infer from spectroscopy. These are not background uncertainties. They are active forces that can create false positives or hide real signals. Confidence grows when a conclusion doesn't depend on one fragile choice, when it holds under independent reductions, when it makes physical sense, when it persists across checks and cross-checks. That's what credibility looks like in exoplanet science. Not certainty, but robustness. And the last step is the one that keeps the whole field honest, naming the unknown that still matters. The measurable unknown at the end of the story is not vague. It has a name and it has a shape. Stellar heterogeneity, contamination spots and faculae versus true planetary absorption depth. This is the shadow problem. The star is the light source and it is not uniform. If parts of the stellar disk differ in temperature and brightness, they change the star's spectrum. They imprint chromatic structure. And that structure can masquerade as an atmospheric feature in the planet, or distort a real atmospheric signature into something we misread. This is not a philosophical worry. It is a concrete confounder with a measurable effect size. So the tension pair we end on is the most sobering one-planet atmosphere versus star contamination. We can't solve it with confidence alone. We solve it with more and better evidence. Not just more data in the abstract, but specific future data that attack this exact ambiguity. Stellar monitoring that characterizes the star's surface heterogeneity. Additional transits that show whether the spectral features remain stable or drift with stellar conditions. Broader wavelength coverage that can separate a stellar slope from a planetary line structure. Each of these is a way of forcing the universe to answer a sharper question. And if that sounds like slowing down, it is, because the pace of truth is slower than the pace of excitement. This is the quiet awe at the heart of it. We are reading an exoplanet atmosphere from light that barely notices us. We are extracting chemistry from a dip in brightness. We are, in a sense, listening for life-related patterns with instruments that must first be proven trustworthy against their own tendencies to invent patterns. WASP-39b gave us something real to argue about. The SO₂ interpretation stands as the best current conclusion, conditional, tested, defended. But the deeper gift is the method we had to build to make that statement responsibly. The barcode returns one last time. Lines, bright lines, faint error bars like a thin fog over certainty. And the closing thought is not a triumph, it's a boundary between what we can measure and what we want to mean, between detection and understanding, between the exoplanet atmosphere and the star that backlights it. We end where the next story begins, with the measurable unknown still in the way: stellar heterogeneity versus planetary absorption. And with the knowledge that the next time a spectrum offers a hint of life, the first question won't be, is it beautiful? It will be, how could it be wrong?